That's, I have some personal issues that prevent me from traveling, but so I have two talks at NIPS, one at the beginning, one at the end, and I'm not going to stay the whole week there, so go only to the second one. So we'll let you know. I mean, if it's only about, if it's not a majority of the class, we'll see what happens maybe. So I just want to review what I said about sequential decision making last time before we about Wald's theorem or sequential probability ratio test, and just the summary of it was there are some points I really want to emphasize again. So we are talking about a likelihood ratio, a probability likelihood ratio test, and I define the likelihood ratio of a sample of size n, or IID observations coming from either one of the two states of the world, as simply the likelihood ratio at the two states. Of course, the assumption was that I know the probabilities, and therefore this is a well-defined function. I mean, I simply apply it to any sample. But notice that this function, of course, is independent of the state of the world. I mean, it doesn't assume anything about it. So once I know the probabilities, and I assume IID, I mean, I assume that they are independent, but they don't need to right now, then this is a well-defined function, and if they're independent and it's a product, if they are conditionally independent, which means that every state of the world I sample them independently. As I said, it's actually, it doesn't imply, it implies that they're not unconditionally independent, but that doesn't matter at this point. And then what we do is we look at, sometimes we call it the log likelihood ratio, which is just the log of this. And this log is a sum of IID numbers in the independent case. And we look at the log likelihood ratio as a function of the number of observations. And you see that my colors are old. Okay? So this LLR of xn, which is again a function of the sample only, which I can calculate, is going to make what we call a random walk. I mean, it's going to be a sum of independent random variables. So it's some sort of a random walk. Or if these variables are normally distributed, sometimes call it a winner process. Or in another context, if this is called Brownian motion, it doesn't matter. It's the same thing. So, and this is going to accumulate with a positive slope if I'm in the first state, and with a negative slope if I'm in the second state. But it's going to be a random variable, which means that it's going to have fluctuations, ups and down, depending on the variability of my two distributions, actually. So, but what we said, what we proved, is that these numbers is going to accumulate with a positive slope if I'm in the first state, with a number which I called as D01, which was the KL divergence between my observations in the first state or in the zero state to my observation. So if this is a positive number, which means that this happens whenever the two distributions are not identical. It can be a very small slope, very small number, but it's always positive if they're not identical. It's zero if they're identical. Well, identical up to a set of measure 0. So, and of course, it's going to decrease like a random walk with a negative slope, which was minus D10. So you can define it exactly the same way, but I switch between the two distributions. Okay? So these numbers are actually very interesting. I'm going to call them the information gain rate or sometimes call it the information per sample that I actually get during my, and you see that the slope of this curve is going to determine eventually how fast I cross any threshold here. So, and the average number of samples for which I cross the threshold is determined by this slope. So, given the two thresholds, which I call log A and log B, and these two thresholds depend on the two probabilities of error, alpha and beta. So, for every choice of thresholds like this, there is some probability alpha and probability beta of the two types of error. So, whenever I choose this threshold, I select the two. Whatever the thresholds are, there are numbers alpha and beta associated with them. Of course, the threshold may depend on the properties of the distribution as well. But so if I ask you, for example, what is the average sample size needed, or what is the average number of observations I need in order to cross a certain threshold? So what is it? It's simply the level of the log threshold divided by the KL divergence. The KL divergence of the slope is simply A, or log A, divided by the number of samples. Okay. So once you know the slope, once you know the rate of information, you can estimate what is the sample size needed in order to reach that. So these are important numbers, those slopes. Of course, the fluctuations are also important, because they determine essentially the stability of this test, or the robustness. But at this point, we're not going to talk about fluctuations. Fluctuations depend on the second moment of the log likelihood ratio, on the variance. But at this point, this number is beyond the scope of this course. I mean, actually, an interesting number. There are many things to say about it. So at this point, we don't care about fluctuations. So those, if you actually want to say something interesting about the robustness of this test, I mean, how confident I am that this sample size will be enough, I need to know something about the variance. But if I talk only about the first moment, about the average number of samples, this is given by this numbers, positive numbers. So this is why those KL divergences are so important. And what we showed is that if alpha and beta are smaller than half, then what's that greater than 0? Then we know that A should be greater than B. We actually showed, and I hope that all of you are now convinced that this is less than 1 minus alpha over beta, and this is not greater than alpha over 1 minus beta. So this essentially was my main calculation in the last hour, and I don't want to repeat it. It's very simple.
Yeah. On that curve, so each point on the curve is the probability of an entire sequence, or is there the probability of a particular observation?
So each point of this curve is the log likelihood ratio at a given number of samples per particular sample. So this is one instance of sample. On an average is going to have different samples. So just reverse, just permute the order of my samples to look different.
So it's actually given, it's the probability given W1 or W0 and all of the previous observations.
No. So the probability ratio is defined by the fact that I know the true distribution. Okay, so the whole assumption here is I have this true whatever distribution. I give it the stroke of convenience of Gaussian. Anything. So let's say this, I know this distribution. So I can calculate this ratio for any sample. Okay, so it's a function of sample only. So now I look how does this ratio behave when in two cases, in the case that the sample is coming from first division, in the first place, or the second division. If it's coming from a different distribution, I don't know anything about it. Right? I said that in these two cases, I know that in the first case, it's going to grow linearly on average. This slope, and second slope is going to decrease linearly with this slope. Now, what's the question again?
Yeah. So it's growing though because you have the previous observations.
dependence between current observation and previous. That's why I factorize it into product. Turn each one of them is just the log likelihood ratio of this particular sum. And because I sum them, I sum those random terms, I get this fluctuation. Sometimes it's going to decrease, sometimes it's going to increase. But I know that on average it's going to increase. In the first case, it's going to decrease. So again, the question is not really. It's something else which is.
If they're IAC variables, it should just fluctuate around the mean, right? Unless you're doing some sort of normalization by some sort of overall.
No. So
if you're just taking a random.
I said that this log, I know that this log likelihood ratio is going to be on average. Sometimes we wrote it, let's say, topically, it's going to behave like n times the decay between whatever. So n is here. Okay, so this is why the slope goes like linearly. This is n, the number of observations. It's going to go proportional to n. That's what I mean. Of course, if you divide by n, you get the average. But the slope is going linearly. That's the problem. Yes.
To compute the average and the boundary A cross, one cannot just read the ends in the graph, right? I mean, it makes kind of sense that, okay, after n samples, that the average, average log.
Well, I'm not sure exactly if you have
I want to know.
This question or not a this question. Of course, you are right. This is a random number, and therefore the point of crossing the threshold is a random variable as well. It's going to have some spread. Okay? Which depends on the fluctuation. So if all the KLs are the same, then it's going to be more or less, it cannot be, because some of them must be positive, some of them must be negative. So it's not always, even if the distribution are very close, because of these normalization issues, the ratio is always sometimes positive, sometimes negative. But what I'm saying that if I'm sampling it from the top distribution, I'm going to sample more often positive part. If I'm sampling it from the lower distribution, the numerator, then I'm going to sample more often the negative part, and that's I think the reason for this. But so it's kind of deeper than what it looks. There are many issues about the size of this oscillation and what happens if I cross, what is the probability if I cross it before or after I average n. But all these things is hidden in the probabilities of error. Essentially, the probability that I cross too soon, or that I cross too late, or that I cross the wrong threshold, it's all buried in this alpha and beta. That's why alpha and beta are important. But what we said, what I showed you last time, was that no matter what the probability ratio and what the probability distributions are, these two thresholds are always bounded by these two numbers. And so the trick, or in practice, as we say, I guess, the reason, well, actually most people take these two numbers to be the threshold. So we know that we are outside of this interval, so we're having a more robust test. Which means we need more samples, but not that much more. Okay? So let's say, because it's running logarithmically, essentially what these things are telling us is that asymptotically the probability of error is decaying exponentially with this 0, 0, with these two numbers. So you see that when alpha is very close to 1, this is essentially 1 over beta, and when beta is very close to 1, this is essentially alpha. So let's say that I...
Zero, not one. Zero.
What's zero?
If alpha is close to 1, then it's close to 0.
I'm sorry, plus alpha goes to 0. If alpha is small, 1 minus alpha is close to 1. Alpha is very small, so I'm talking about small error, let's say 1%. So this is 0.99 over beta, so this is always smaller than 1 over beta. And this is always larger than alpha. Because I divide by small number smaller than 1 here, and multiply by number smaller than 1 here. Okay. So you know that alpha asymptotically grows like, so log alpha, so essentially I can write log alpha here, and you know that log alpha essentially, so I can put even higher bounds here, log alpha and log minus log beta. And these are telling me essentially that alpha and beta are both asymptotically growing exponentially with these two exponents. So actually, that's a very strong result. It means that if I increase the sample size, the error decays exponentially with the sample. So IID observation are really a very strong tool if I can actually afford to have it. And I can't exaggerate the importance of this, because this is really the reason that eventually you can make satisfactory decisions in a very noisy environment. Even very weak, in the sense of weak information gate per sample, this exponential growth or decrease, if you want, of the error is telling me that I'm going to be fine eventually. So just increase your sample size by a factor of 2, and you exponentially pass better in terms of solution. Okay? So this is an important lesson, and it's really going to be a cornerstone in many things that we're going to do later. The fact that we can actually have almost certainty, even in a very uncertain world. I mean, just wait long enough in terms of integrating the information. We're going to have, that's really what saves us from the noise and the specificity, randomness of the world around us. With all the dramatic way I'm saying, it's really important. Yes. I don't know how long.
Yeah, you don't know how
So
what sample size you need in order
No, I actually do, because if I have some information about these two numbers, D01 and D10, I can bound them, and then I can guarantee. Now, notice, by the way, that this is called the perfect test. I mean, this is the best I can do. This is the base optimal or the Hamilton optimal test, the log likelihood. But what if I don't have the right distribution for some reason? So let's say I have some really lousy model of the world, which means that what I actually plug here are not square distributions, something different. I didn't learn it correctly. This is going to take me to the next step, the estimation problem. Then, okay, so maybe I'm wrong here. So maybe there's a factor of 2 that in the DKL that I actually think I have with respect to the optimal. Not so bad. So despite this many observation, I'm going to test it. As long as I manage to get something which is informative with the average, that will be okay. And we'll come back to this. This is an important thing. So sometimes we can use really lousy models. It doesn't have to be optimal. Life is never optimal. Biology is never optimal. It doesn't need to be good enough. And good enough in this case is that my decision time is fast enough to be relevant for what I need to decide. When I will avoid something on the road, I have a few hundred milliseconds or less, I don't know, but I need to make a decision, 2 seconds, or 3 seconds, whatever. During this time, I have to accumulate enough information to make the right decision, and even if I don't have a perfect model of the world, it's enough that I have some information given. And that's really an important flip. Okay, because then once I have some information gain, I can make my decision essentially as reliable as I want with only linear time correlation. Okay. Remember this. And okay, so you have some exercise on this language exercise, which you really should demonstrate if you already started to do it. Just sample letters from text independently. I can very, very quickly decide very confidently between 2 languages if that's sufficiently different. Language can be anything, I can make a decision about the person I know, or whatever binary decision I need to make, it's sampled information. You have very weak information. For example, you take an image, and if you take X to be some features of color or texture or whatever in the image, very, very coarse-grained information, as long as there are some differences between is a face there, there's no face there. A very loud statistical test like this will give you a very quick, very reliable decision or estimation of what it is. Okay, so that's this. Now, we want to extend it. So actually what I want to do now is to introduce some language that is becoming more and more popular in statistical modeling, which is called probability graphical model. That's graphical model. Sometimes they're called not exactly the same thing, but very close Bayesian networks. Actually, these are sufficiently important things that we actually use them. There's like a whole course in website, it's not really every year, obviously, because we don't have the right teachers with us right now. But we have a course on graphical models in computer science and large function learning, which I highly recommend.
We theoretically have it.
We
hear that for 3 years we've been hearing that it will be
unfortunately,
given.
Valerie Dan and Gabriel Gosson used to do physics, so not here. There are other people who can do it, like Yair Weiss and Neil Friedman and others, but not so also. So we'll teach this course. At least once every 2 years we promise to do this. I don't know. It's not up to me now. Anyway, so graphical models essentially, it's also some sort of way of thinking about neural networks. And actually, it was born as some sort of mathematical computer science way of thinking about neural networks, but it's more general. It allows us to express a lot of other relationships in variables. So notice that what we had so far, so graphical models is a graphical method, which means, okay, we write graphs. But when we say graphs, something I actually take it seriously, and so there's a whole mathematical language that goes with the notion of the graph, which I'm sure some of you have heard about, but it's not going to use graph theory in the sense of the combinatorial side of it, but actually in a very simple way. So we take graph in our language as a mathematical object that has essentially two types of objects in it. One is what's called nodes, or it's called in, or something like this, and the other one is called edges, or things that connect nodes. Okay. So this is a graph in general. The edges can be indirected without any error on it, or can be directed, which means I'm thinking only in, and then it can be symmetric. Not only, there are many things that we say about graphs, but all I need now is just a particular picture. So imagine that so in graphical models, probabilistic graphical models, we assign to every random variable in our model, in our picture, in our description of the problem, a node. I always denote it like everybody else with a circle, and actually sometimes it's a square or other things. Usually a circle, and I just put the notation of the variable on the node. So in this case, the first node that we had was the world. Okay, I think the world of omega has this two states in it. So the instantiation of the world of omega zero. Or W. Now, the other variable in our Bayesian decision problem was what? A will come later. Was the observation. This is really important. So, and these two nodes were connected in the sense that if I have an error here, when edging this graph, I assume that there is some probability connection between them. So the first axiom, or the first rule of Bayesian or graphical models is that edges represent dependency, statistical dependency. So if they are independent, I don't run it. There are no edges. Okay. So as long as I didn't put an error here or an edge here, W and X are assumed to be probabilities, which are variables that are independent from each other. So, and actually having our statistical model, we have this prior omega. Sometimes we write with a zero here, but it's really not important. And we had the conditional probability. And since this is there's an error here, we know that X depends on it. Essentially, my model graphically is just written in this simple way. This is the statistical model. A node omega, and an error, in this case a directed error, because I always assume that I can is what I call the statistical model of the world. This is the distribution. Okay, so we now think about it as a graph. Now, of course, there were other things in my problem. So once I knew x, I generated from it something which I call the decision rule, or the action, and then essentially infer something about honesty. Okay, so, but this is not, strictly speaking, it's not an error in the graph, it's kind of a funny error. Of course, I could, in principle, think about it as a non-deterministic rule, so some probability. So, in some sense, the way I should think about it, so there's another node here, A, which is the action, and it depends on my x only. And then there is something which is some sort of interaction between the state of the world and the action. So this node was essentially my decision rule, or in general my probability of doing an action at a given state, at a given observation. This was my policy or decision rule, so this is the way I think about it. And what connected these things? Is my picture. So essentially, there was no real error here, but there was a lambda. Even a W or the cost. So to say that now I'm mixing things, because somehow if I want the error to represent probabilities, lambda was not really probabilistic, but it's actually another random variable. This was deterministic in our case. By the way, I think you can easily extend it if you're giving, by the way, stochastic rewards, like our salary. And you get every month something different. So it's really an unpredictable variable in these notions. So we have some variability in our reward. Then of course I have to put everything about average it somehow respect everything in order to talk about expected. That's clear. Just as if we have a policy here, we have to average all these statistics. So everything is averaged eventually. Okay, but this is not really what we do in the Bayesian decision world. Actually, what we actually do is something different. We have the world here at time t. Like I decide about my umbrella in the morning, but actually I want to predict the weather later on, let's say tomorrow or the next day. So actually, there's another variable here. The world at time t plus 1. So everything here is turned into a stochastic process. And the assumption is that there's some sort of relationship between the weather now, from which I take the observations, and my weather later, where I'm actually going to test my prediction. So actually, the real formal thing that I was doing in my umbrella problem, on any prediction problem, is really a prediction problem, in the sense that I have an action, and then the action interacts with the world. Essentially, when I put the umbrella above me, I'm protected from the rain. And this is, I'm changing the effect of the world on me. Yes.
In that picture, taking the umbrella would influence the weather.
Well,
No,
so
like you draw it, like no.
So to me, to be strict about it, you can think about the weather on me. Whether the rain is going to hit me or not, that's what I really care about. And this is actually influenced by that. Okay. But you're right. I mean, in general, it will affect the weather. And whatever I do affects the state of the world. Yes.
The error between A and WT plus 1.
Good question. So here so far I didn't do anything. I mean, so far we assume that if I know my prediction, I didn't even take this into account. But actually, obviously, I mean, implicitly in everything that we did so far, there was an assumption about the connection between the weather now and the weather in 10 hours from now, or 8 hours from now. Usually we assume that this assumption involves some probabilities, because it's not certain. So there's some probability here. Okay? Some conditional probability that tells me what is the connection between the state of the world in time t plus 1 and the state of the world at time t. Now, of course, in reality, the state of the world until time may depend on many, many other things. Around the previous state of the world and so on. But this very simple assumption is already something which we call a Markovian assumption. So we are going to assume that, and that's like the simplest and actually very useful assumption, that the world is Markovian assumption. That the state now of the world depends only on the previous state. And those of you who learn some physics know that essentially this is just like saying that there are laws of physics which can be expressed with finite order differential equations. Exactly the same function. So since all the laws of physics that we know now, even the very sophisticated ones, are expressed, or at least believed to be expressed by differential equations, like the second law of Newton, or like Schrödinger's equation, or like the wave equation, or whatever it is that you encounter in physics, or in physical sciences. This is essentially an assumption that there is a state and there's a first order condition. Even if it's a high order differential equation, I can always turn it into a first order equation by extending the state. Now, for those of you who don't know what I'm talking about, forget it. But this essentially is the Markovian assumption. Okay, so we'll come back to this type of model. This is actually already something which we will call later an MDT. So essentially this is what we did. We didn't explicitly write this because we assumed some sort of continuity. If I know the probability of rain now, and under this observation, this is going to be the same within some interval of time. But implicitly it was always there. Why should I measure the clouds or listen to the radio this morning every day again? The weather may change, roughly change. Okay, but this is to see that there's already some power in this type of expression. This graphical representation, it makes organizes things somehow. So, and actually, of course, in this case, if I actually write a model like this in the way I wrote it now, and I really take the errors seriously as condition of probabilities, so what I actually should have is that the probability of the world at time t+1 depends on the previous probability. Depends on all its parents, I mean all the things that point to it from the past, and of course also the A. Now this becomes x and t of t and A of t. And so this is really the assumption. That the state of the world depends on the previous state of the world and my current x. So that's very nice because so I know that this node has two arrows coming into it. And these two arrows would summarize all the variables on which it depends. That's the point. So if I have two arrows, conditionally it must depend on this. Okay? So this is, again, it's a very nice expression. So this every node is associated with variables, and every arrow with some sort of condition of probability. And now I'm more or less covered. That's all I need in order to work with it. What is nice about this graphical representation is that I'm gaining something. I'm gaining something from properties of graphs. When I combine them with the laws of probabilities, I can express much more easily many ways of working with models which are not so easy without them. So let me give you the first non-trivial. So this was the simplest possible model was a state and an observation. Now, I said already that the state may vary with time. Okay, what happens with the weather? Actually, there are much more interesting things, like, for example, my speech now. So think about it. This is an acoustic wave. I mean, some vibrations of the air. This is generated by my breathing and eating mechanism. I mean, my vocal tract and my vocal cords and whatever it is that generates the sound. But it's actually, and it's changing all the time because I'm changing the parameters of my vocal tract and my vocal cords and so on. So I'm generating a very variable sound. But the fact that this makes sense to you is because underneath or behind this sound, there is something else, which is like phoneme, or a vowel, or a consonant, or a word, or whatever, or maybe an idea that I'm actually trying to express through this sound. So when you think about it, this is a random variable which depends on some other state which you don't see directly. Okay, so this is really the motivation for thinking about the model like this. The state of the world is a variable which depends on time. In this case, I'm talking about discrete time, but not necessarily, it's not really an invitation. You can make it continuous if you really want to work harder. But, so I am having a discrete time steps, 1, 2, 3, whatever. And let's say that these are my phonemes or my the things that I'm actually trying to produce with or convey to you through my speech. Or if you want, these are the words that in every day, or every 6 hours, or every something that you consider as relevant variable, time integral, which may actually be a variable on its own, but that's the story. And then what I have is a variable xt, which depends on the state only, and so on. It can continue forever. This is already a different type of model. Essentially, I'm just extending my very simple world state observation into a vector, and into what we call stochastic variables, or stochastic processes, which are essentially things that change with time. So I don't know how many of you heard the name, the term stochastic process before? Not all of you? Okay, so stochastic process is a random variable with function of time. Essentially, it's a sequence of random variables, which may or may, well, actually, strictly speaking, I need to be able to write the joint distribution of any finite set of these variables at a finite time. If I have a joint distribution like this for any finite selection of indices of time, then it's a process stochastic. So, for example, a Markov chain is a stochastic process. If it goes forever. Gaussian or random white noise, I don't know if you heard about it. Gaussian process in time, maybe certainly heard about it, is a stochastic process. Of course, a stochastic process is a random variable which has parameters, statistics, and so on to talk about. Okay, yes?
Just by understanding this specific graph, is there a dependency between xt and xt plus 1?
Well, only through the state. That's the whole thing. So again, that's exactly what it means. Good question. What these arrows mean is that the observations are conditioned on the state are independent. The only dependency between the observations is through the dependency. Okay, so this particular model is a very important class of models which are called hidden. Okay, I'll explain it in a second. Hidden Markov models. Usually just say HMM. HMM, that's what it gives hidden Markov model. And so it's not hidden here. It's going to be hidden when I actually don't see the state. I have to estimate the state. Actually, this was also a hidden Markov model in some sense. The very simple base estimation problem, because I didn't know the state. I still holding the observation. I had to get a decision based on the observation, but I didn't see the state. The state was hidden. If I could see for certain the state, if I could certainly see the state, then I don't need to observe anything. So the state was already hidden in the base decision. So, okay, so what is nice about this is that now I can actually write the probability. If I have the graph, I can write an expression for the probabilities of everything that I want to know. So, okay, so we can write a probability function. So the joint probability, let's say that there's some initial state here, W0, it has some prior, but that's not really important. If I start somewhere, it's actually going to be less important, I think, but in principle, that's what we have. And so the probability of, let's say, W0, X0, W1, X1, and so on, still at some large T, Xt. So let's say I have finite sets of observations in state. So this joint probability distribution has many variables, can now be given the model, given the graph, And the syntax of the graph, I mean, we know how to read it. So essentially what it means, there is a Markov probability distribution here between every two. There's transition probability, as we call it. This is what this arrow means. And we assume it's 3/6, the same distribution everywhere. That's of course an assumption we have to make explicit, but that's what we assume. And there is a observation probability, P of x given W at every t. And that's it. So this factorizes immediately. Okay, let's write it like this. P of W0, P of x0 at W0, and then P of W1 given W0, P of x1 at W1, and so on. So you see what I did? I just I assume this graph. And so everything else is independent. So the only thing which really depends on each other is this on this previous one, and this on this. So I can factorize the whole distribution as a product. So I can write it there. Now I have P of W0 times the product, P goes from 1 to T, P of WT given WT minus 1 times P of xt at W. I actually omit the substitution. Something. Okay? If I want to just denote that PW0 given W minus 1 is PW0, just and I can write 0 here. Okay, so now this is nice because it's a nice product. The problem is that this is what we call a fully observed Markov theorem. We can actually see both. But the problem is that we don't see the W's. We don't see the W's, so we need to modify this a little bit. And so what we see, what is the likelihood or probability of the observations only? So the probability of x1 to x0, x3, x1 to x. This probability is what? So if I know the full model, this is the model. This is the argument. This is what the model tells me. If I know the full model, what should I do in order to get only this? Correct? What should I do in order to get only this? Yeah, so I do what we call marginalization. So again here, the probability of observation, I have the joint distribution. The probability of observation only is simply the marginalization. It's always true. So whenever I have a joint distribution, I can marginalize it in sum or integrate over all the variables that I don't see. That I don't know. That's a very powerful trick. Because whenever I don't know, integrate over it. As a physicist, you usually say trace over it. Take everything that you don't know and average over it. Okay? So this is going to be the integral or the sum over all the possible states of the joint distribution. Let me just write it like this to save time. So this is the whole sequence, which is what I just wrote it down. Okay? So I can rationalize, which is going to be the sum over all the W's, which I don't know, of this product. And it allows me to ignore the prior first, so I can just make sense. Or assume whatever you want to make it to make sense. Okay? So it's the transition probability multiplied by the observation. Okay. So this is not so nice. Okay, so essentially this is what, as I said, in physics, just like trace, maybe you see this in many. It's the same thing. Usually what we have there is matrices, identity matrices, things like this, and the trace down number. Okay, so we use them. So if you see this, don't get scared. The same thing. Now this is not so nice. Why is it not so nice? So it's not a product. It's is a headache because I can't take logs. I can take logs, but the logs don't sum. It doesn't factorize, and the log doesn't get it into simple sums. Okay, so this is going to cause us a headache, but in principle, we know everything now. So we can actually ask the problem in HMN that we usually ask: what is the most likely sequence of states given my observation? When I think about the example of speech, this is what you do when you understand. Not exactly, but at least implicitly, that's what you do. You probably don't do this at all, but that's what your brain does for you. I mean, you don't really write a Markov model there, but it's implicitly done. And essentially, when you decode my speech, trying to understand what I'm saying, which is not always so easy, is essentially finding the most likely, or something like this, state sequence, solving the decision problem. But not about one state with one observation or with one sequence observation, all the sequence. And this actually is going to generate a sentence or a piece of speech that eventually makes sense to you, hopefully, at some point. Okay. Yes.
So we don't know the identities of the omegas in this model, right? So WT could be W0 or W1 and W2.
Can be one of the set of, let's say in the case of speech, one of the set of phonemes. How many phonemes actually have in speech is the question, but let's say most people agree about something. 40 phonemes in English. Okay, so it can be one of those states which you're trying to encode in your sound. You encode it stochastically. Actually, many things for which this model is not correct, but this used to be the standard model of doing speech recognition for many years, and it's still until the deep learning stuff took over, and it's still the most a very powerful way of thinking about statistical models. So, but you see that we already have a problem here because we have hidden states are hidden. Hidden states. That's why I'm considering them. Because we have hidden states, the product goes into sum of products, and sum of products is a headache for taking logs. Okay. Maximizing sum of products can be a headache, and we need to invent something. And we'll talk about it. Some mechanism for doing it. I can tell you this is a hard problem that is not really solved in general. Now, okay, so my time is up. I want to talk about another graphical model, which is the Markov decision process, and what's called partially observed Markov decision, but very briefly in the next 10 or 15 minutes. And then I'm going to start with the problem of how do we learn these models, how do we estimate from these models. So this is going to be a dense class today. Now, you're not asking enough questions, so I assume that all of you are with me, but it's probably a wrong assumption. So please ask. Okay. בניגוד ללרני שאנחנו קצת סוגלים מסוכר חדש.
אתה רוצה לדעת מה הלייבליהוד של המחקר, נגיד שאתה רואה בנט. אתה אומר, טוב, בסדר, אם הייתי יודע כל אחד כזה מאיזה גרמה, מה הייתה הריאליזציה של המטבע שבחרת לגרפיאן, אבל הייתי יכול לכתוב את זה פשוט כמכפלה של פונקציות של ליבוד נורמלי. אני לא יודע, כל אחד כזה, אני חייב לעשות תרבות שלמה. שם זה יוצא, כאילו, שם זה יצטפו, כמכפלה. רגע, עכשיו את זה. לא, אבל מה אתה מקבל כמו שלא? זה מה שקיבלנו, זה יכול לעשות, בדיוק.
חלום הזה. הסתכלתי על כל הערכים של ההורים. זה סתם W1 עד WT, ו-X1 עד XT. לא, לא הייתה אותו, אני מתכוון תמיד, שאני כותב כמו וקטור, אני לא בפסקה. זה לא דבר, כתבתי את זה מפורט, זה אותו דבר. אלה שאלות קלות, שאלות המעניינות. שאלות יותר חמקות.
כמה סוגים כן, נכון. אבל נראה לי אחת השאלות איפה אתה למה ואיפה זה קורה? לא, זה מה שאמרתי לו בהרצאה, כאילו שמדברים על השוק שיהיה קורס עוד פעם ב-PGM, באמת מדברים על משהו, כאילו זה משהו כל הזמן, כאילו עכשיו גם אומרים, כן, באמת זה שם של קורס מעולם לא ניתנו אינו ניתן למתי יושב כאילו לנסות להסביר לך כאילו נקבל קיווינו שזה יהיה שונה כי היה באיזשהו סיפור יש, אבל כאלה שהיו נותנים פה
הוא אמור לחזור שנה הבאה.
אומרים את זה כבר
לא, פעם בין.
כן? כאילו, אנחנו בעצמנו ניהלנו את השיחה הזאת שנה שעברה. כאילו, וגם אז זה היה אותם אמירות.
דיברתי עם מה מביאה את העינה שלו שהוא עובד שם עכשיו.
בגלל זה אני אומר שהוא לא היה. ולא בטוח בתל אביב.
כן, לא בטוח.
אז כאילו, יש את ניר פרידמן שכתב. אשר כתב את הספר בנושא, אבל לא נראה לי שהוא יעביר.
הוא מעביר אחר, גם כמשהו.
לא בביולוגיה. כאילו, הוא תיאורטיקה. יש את הקורס, את הפרקטיקה על משנה קורס הזה?
נכון.
אז תכלס כל החלק הראשון שלו זה קורס בדברים של דלתה. נגיד יש שם דברים שאתה מדבר על כאילו על NLP, אז זה הכל על NLP.
זה אומר שזה מתקדם. לפני שנתיים זה היה...
מה? מעל 30 קוד, אתה יודע.
לא נותן לי תחושה הזאת.
שאלה של דאטה סיינס.
שני שיעורים ראשונים, שני סיפורים.
כן, רק סיפורים סיפורים, אבל דווקא כאילו זה היה טוב.
כן?
אז זהו, זה בכל זאת מה שלכם שם השנה. בטח. עכשיו אורי אבני. זה נראה לי קצת השתנה, כאילו, בחוץ נורא גדלו לחמש אנשים ובאו לשיעורים. זהו, הם פתחו את, בגלל שהם פתחו את זה עכשיו.
לא, זה.
כנראה אתה היית היחיד, כאילו...
לא.
פשוט
לפני שנה לא היה.
לפני שנה לא היה, לא היה.
לא.
אבל גם המפגר אמרו שהוא היה בחו"ל.
המפגר היה שנה בבוסטון. לא מצאו...
וואי, כן.
אני מבין את הדברים לא.
לא, בסדר, הם אוכלו אז, אבל כאילו... הסתכלתי בקישור, וראיתי שרשומים מלא אנשים סגורים. כזה...
לא, תשימו בזה. שלא, גם אז
לא, נראה לי בזמן. כי בעצמם אמרת על זה אנשים, אז אנחנו נעשה תפקידים לא להגשה.
לא, אין בעיה.
כאילו, נעשה תפקידים לא להגשה, לא, זה מה שהוא אמר בהתחלה. אבל איך הוא מצא בו את זה?
All right. So I just wonder, how many of you heard about HMMs before? Actually learned it? I mean, saw the algorithms? Okay. More or less. Okay, so don't think that I'm teaching you HMMs. I'm just mentioning this because these are the kind of models which we work with, and actually I find HMMs extremely useful for brain science in general. For example, estimating the hidden states of the brain, given what we know about it, is an HMM problem. Because unfortunately, models like HMMs, and even simpler models like state and observations, when we don't know anything else, with hidden variables are in general difficult. We don't have an optimal way of doing it, but this is true for most interesting problems. Generally, in the worst case, very hard. We still have to live with them. Okay, so the other model I want to mention here, and we'll come back to it later on, what to do with it, is another extension of which I already mentioned here already, more or less. And this is, here there are no decisions. I mean, here it's only a statistical model. There are world states, and there are observations, and our problem is there can be many different problems here, but the most standard one is to infer or to deduce the states given the observations, or to guess, to estimate it. But there's something open here somewhere, which disturbs not only me, I suppose. And of course, the real question is, okay, how do you learn these models from observation? How do I build a model for speech, for example, or for whatever it is that you're interested in modeling? Another model which turns out to be very, very important for many applications, it's called Markov decision process. or extension of it, which is actually a combination of HMM. So as I said, it's already written here. So here there was no decision. I didn't have to estimate anything because there are no actions involved. It's only an estimation problem or an inference problem. But in life, or the kind of really generalizes the problem that we have with the Bayesian decision problem. As I said, decision is really the most interesting thing that we have to think about. We have world states, which are Markovian. And as I said, assuming discrete times here is not a big deal, although it looks like something important. It simplifies things, but it's not something that you can easily generalize to continuous time if you know how to do this thing. So we have a Markov world states. And again, those that think that this assumption is strong, it's actually not that strong. Some people make a big deal of reduction in displacement. It's not, because usually we don't really see the world. So assuming that it's Markov, it's assuming that we know actually the state of the world now, unless I know, in physics it means that I know the position and momenta of every particle in the universe. Okay, that of course is nonsense. I never know that. So there are always variables I don't see. So essentially, even in physics, unless I really have an isolated system, which is completely independent of anything else that happens around, I don't really see the state of the system. But so this is a formal assumption which makes life easier statistically, but it's not that crucial. But then let's say that I'm actually doing an extension of what I did here. So there's an observation coming from each state. Let's call it xt. Put it a little higher. And this affects some sort of memory, which I want to call empty. Or I actually register it somewhere. I write my observation in memory. Right now it looks trivial. Okay, so you remember your observation. What it will, if you think about it as something like the state of my brain, it's not so trivial. I mean, what is it that I'm actually registering, remembering from my observation? And then I act. I do something like an action. And as I said before, I can think about it as a random variable. And then this affects the state of the world, as before. But then I do it again and again. There's a new observation, xt plus 1, which is going to affect my memory times xt plus 1, which is going to generate another action, t plus 1, and so on. Okay, it's not such a nice picture, but you know what I mean. So it's exactly what I said here. I just introduced another variable, which is the memory. But so essentially, this is something which begins to look more like what I really want to study. So the world is changing, and I'm seeing something from it. So this is some sort of sensory input. And I'm then acting on it. This is actions. But I'm not acting just once. I'm acting on every observation. Actually, the observations can be many observations, as before. I mean, I can wait before I act and accumulate information. Just think about driving. You accumulate observation, then you do something. You move the wheel, you brake, press the brake, whatever. Yeah. Okay, that's a good question. Not right now. So you see that something is missing here, because obviously what I want is the memory to affect the memory, and this will come next in a moment. But so this particular model is my way. It's not. I'm not going to see it in many books, but this is my way, and some of my colleagues. That's the way we think about MDPs. So in something I have something like an HMM here, but this is not really MDP. It's already what we call POMDP, or partially observed Markov decision process. So if I don't see if the state is really hidden from me, then I am in a much more complicated state. This isn't precisely as in the HMM. But let's say that the first thing is that xt is actually MWT. This is what I call perfect observation. I see the world. So if I see the world, I mean, I know what I need to know. Nothing is hidden from me. Of course, I never see the world, but I see the relevant part of the world, the thing that I really am acting on. Then it's called Markov decision process. I see the world, but the point is that my actions affect the states. Okay, so this is a slightly different type of game. Here, the states were evolving in time Markovianly just according to the states. There was nothing that I did that affected the state. It's like my speech. I mean, it's not really true that nothing that you do affects my speech, but the first approximation is true. But especially if you hear the radio or something like this. But or listen to music, let's say, this is something that an AGMM is a good model for. But if you actually play music, let's say, play with somebody else, then you're an entirely different type of model. I mean, what you do affects what the other person is doing, and you're actually part of the process. Okay? So MDP, or Markov decision process, is trying to capture this type of dependency when my actions actually affect the states. Okay? So, and you see, it's only partial. So what I have here is what I wrote before. I have the probability just at the state t plus 1, given the state at time t, and my action. I have the policy, or the action selection principle. And I have the observation, which is how my memory depends on the observation. At this point, this error is missing. The crucial, how the memory depends on the memory. I'm going to add it in a second. But this is, so I have observation, and I have the observations given by the state. This is a channel. This is this probability here. Each one of those errors should have a condition probability attached to it. Now, I assume perfectly observed state, a world, is essentially xt, not necessarily W2, it's a one-to-one function. Maybe I represent it differently. But if I can reconstruct the state of the world exactly from my observation, then I said I have a perfect observation. Okay? You see that you can easily, and actually you should relax all these things a little bit, but all such relaxation usually makes things much harder. Now, in this case, here's a Markov a graphical model where the parameters, the distributions are this one, this one, this one, and this one. Okay. So essentially, I have to know all this distribution, by the way, how the observation depends on the state of the world. I usually write it as sigma, and this I write as pi. So there's a channel, and of course, how the memory depends on my observation. Here is also trivial. I just register it. So this essentially is saying I simply have perfect memory of the perfect state. So in the MDP, we actually assume that MT is the same as WT. I really see the world and remember it. Perfect memory, perfect sensing of the world, and only the action is really interesting. But you see that this type of model is already introducing many of the problems that we want to study. I have to make a sequence of decisions. That's the point. So it's not one decision, it's a sequence of decisions. But if we are right and we develop the general theory of decision making, then the same formalism, the same Bayesian decision theory should work for us here. So I don't want to take too much time on this because I'm going to come to it in an exercise. But this is actually a very easy model, the MDP. So there is an algorithm called dynamic programming, which is very general, but in this particular case, dynamic programming solves the problem. I know how to make an optimal sequence of decisions. And of course, there's another thing here. Every one of those transitions has a cost or a loss involved in this junction. Whenever I act in the world, with the world, there is something that I pay, which is just a generalization of the cost function that we had in the decision making. So the goal of Markov decision processes is also known as reinforcement learning in different contexts. Reinforcement learning is a very, very important paradigm that if you didn't hear about, you will hear in brain science and many other places. So it's essentially the same as Markov decision process, in order to, the goal here is to maximize the expected future reward over all future, given current state. Okay, so how exactly you write this probability? So maximize over actions, usually. What should I do in order to maximize my reward? So this is a very well-defined optimization problem. It turns out to be easy, in the sense that there is an optimal solution which can be efficiently calculated using linear programming, and we're going to do it, not now, in about 3 weeks. Okay? Now, the really interesting model is the one where the memory has memory. When the memory actually remembers the memory. Where the memory is actually depending not only on the last observation, as if nothing else happened, but also on my present memory. So if I add these arrows, which means that I'm not assuming this, I'm assuming that mt plus 1 depends on mt and my last observation. Then I have, and if I don't assume fully observed, that let's say the observations are noisy in general, then I have the more general, which we call POMDP, the more general model, which we call partially observed Markov decision process. It's simply too long to write down. So partially observed Markov decision process, or POMDP. And this particular model, the partially observed Markov decision process, is really sufficiently general and sufficiently difficult to really deal with almost all the interesting problems in brain science. In particular, I mean, when we think about the brain, I usually have this nice picture. This is the world. This is the brain. And we have two channels, we have observations and actions. And they are, this random variable essentially. The brain is, this is W, this is M, this is X, and this is A. And they really interact in this zigzag model. I mean, the world generates observation, the brain is using its memory and the new observations to generate a new action. The action may modify the world, and then I have a new observation, another new inference of action, and so on and so forth. And this repeats forever. So this particular model, this is what we call the sensing, acting, or sometimes it's called even the perception action cycle, sensing acting cycle. It's really a very important concept, at least in my world. And when you think about it, if I have some statistical model of describing this interaction, I can really do many, many interesting things. For example, language. Two people communicate with each other. So then the world is another person. Let's say only two. Okay, so, and then I can model the interaction, what is an efficient interaction between two entities like this, under all sorts of constraints. I mean, let's say that I have noisy observation. You don't really hear me. Or I don't really understand your action. So here the action and observation, my action is your observation and my observations are your action, and it's a fully symmetric type of model. So this is the model of conversation. Actually, we do it for language. You can think about driving. You can think about playing the piano, whatever you want. I mean, all these type of models can be cast into this framework. It's a very general framework. And as before, all I need to do is to estimate some probabilities. I mean, in this case, I have this conditional probability, this conditional probability, this condition, the sigma and the pi, and so on. If I know how to estimate them efficiently, then I'm done. And essentially, we know already, we have some hints about it. So we know that optimal observations are in some sense efficient in the sense that of Bayesian decision if they're most informative, if they really carry all the information that I need. But in the MDP case, they have to be efficient with respect to my decisions. I mean, I need to, or maybe I don't need to estimate everything. I need to know only one thing. When I drive on the road, I really don't care about what happens kilometers from me. I care only what happens right here. where I'm going to affect the world, and so on. So the whole notion of sensing acting here becomes much more interesting. So sensing, as I said, I mean, the more ambitious people call it perception behavior cycle. Now, if you know how to solve this cycle, you solve the problem of the brain. In principle. Unfortunately, it's not so easy. And it's not so easy because the POM-DP problem is actually a combination of the hidden Markov model, which is hard on its own, with the Markov decision process. So while the Markov decision process is going to be an easy problem, the HOM is a hard problem, it's going to be even harder. But notice, by the way, that the memory here, the update, what is it that I should remember from time to time, is a very interesting question. In particular, if I have limitations, if I can't remember everything, I have to forget something. If I have finite memory, as most of us have, even if you pretend not to. So we have to ignore, there are things that we have to forget or to erase from our memory. This turns out to be a very tricky business. I mean, what is it that we need to forget? So this is going to be a very hard problem. Once I add this channel of memory, there's a whole PhD of one of my students, or folks who just finished, which really deals only with this problem, I mean, limited memory. What happened there? How do you solve this problem? What can you do? Now, if I have unlimited memory, by the way, things are much easier. I again have a relatively easy problem to solve. So there's a tricky thing here is what to forget. It's not what to remember. And when you think about it, by the way, those of you who learn some computer science, how many of you never heard about the Turing machine? Universal Turing machine. How many heard about it? Okay. So to think about it, this is stronger than Turing machine. So you can think about a Turing machine. A Turing machine has a finite automata, which I can call my memory state. It has a tape, okay, which is an environment when I can do only two things with this tape. I mean, I can read and write. Okay, it should remind you something. I mean, I can sense and act. Okay, so I can read a bit from my tape, do something with my internal state, and then generate another bit. Oh, it can be not doing nothing. Also, can rewrite the bit. So this very simple model of an automata reading and writing to the environment, and the tape here is just the world, is, as we saw, it's universal computation, and I can do anything with it. Anything that we believe that can be done by any computer, including our brains. So this is at least as powerful as the Turing machine in general. So even if I have a limited memory here, that's the only finite number of states as a Turing machine. Something like, I don't know, 20 states. It's enough to have a universal computer. And I can read and write whatever I want from the environment, which I have a reliable reading and reliable writing to my tape. And the tape stays the same. I mean, nobody messes with it when I don't look at it. Then I can do anything. This is a universal computer. So a partially observed Markov decision process, in principle, could do whatever a Turing machine could do. Yes?
That's only an assumption that I can basically store information in the world.
That's right. Why not? I always, when I give talks, I don't know how many of you heard me give this popular talk, I always show this cleaning robot. You know, this Roomba, whatever. The cleaning robot is a stupid brain, okay? But it's actually powerful enough to do anything you want. If it can reorganize the dust in my room and use it as a Turing machine tape. Which means it can actually push dust in one direction, keep it there, and actually use it as a reading and writing from my room. It has sensing, it has acting, and it has the tape, which is the dust in my room. In principle, it's a Turing machine. Unfortunately, they're not that clever yet, but okay. So a very simple organism, a very simple brain, if it has powerful enough sensing and powerful enough acting, can do, and the world is large enough that I can write anything I want on it, can do anything. Anything that we know how to do with any whatever device. Yeah. Okay, yes?
Why did you say that it leads to the Turing machine? What makes it...
Because it's actually stochastic. I mean, actually, without any restrictions. it's actually more general in the sense that I allow stochastic states and stochastic observations. So I have also probabilistic transitions. At this point, it doesn't clear why it should help, but it's made. So it's more general in the sense that I'm not talking only about deterministic function. Okay? As I said already, I mean, if you have adversarial environment, then stochastic things becomes a very good idea, but we'll come back to this. Okay, so this is the motivation for what I'm going to tell you next. Sorry, I got a little bit too excited about it, but sorry. So we want to move to the next chapter of the course. Which is essentially how to learn these models, or what we call estimation, or model inference. Model inference, or another, I call it estimation. Actually, estimation is a bit restricted, but it's going to be related to what we'll later call learning. It's a special case of learning. Okay. So, as I said, I mean, so far, in everything I said so far, we assume that we know the model. Somebody gave us the model. P of W, P of omega, and the probability of observation given the model, the action given the observation, whatever it is, we know. And we just had to make some clever estimate of one thing, in this case, the action, which was already actually a learning of some sort. Actually, we call this type of learning decision-making or planning or things like this. When the model is given, we just have to decide how to act. But usually we don't know the model. So we need to develop some fundamental general framework for model estimation. And in general, so we're going to come back to probabilities, but we assume first what we call parametric probabilities. Now, if some of it looks like arbitrary, it actually is. In some sense, I mean, this is the history of statistics. It developed from a combination of first principles and practical problems. And they realized very quickly that this problem of estimating a statistical model is a fundamental problem. And there was a whole theory developed in the case where we have parameters. So parametric distributions, you actually saw already many of them. Let's just remind you some examples. I mean, for example, Bernoulli trial, coin flips. So this is distribution. Okay? Let's say Bernoulli is I. Bernoulli is this probability. The probability of having x equal 0 given theta is theta, and the probability of having x equal 1 given theta is 1 minus theta. And theta is a number, continuous number in 0 and 1. Okay, so this is the simplest, almost simplest probabilistic model I can think of. I mean, a coin flip, independent coin flips. But once I said that there is a parameter, I said, actually, I don't know what this theta is. It can be anything from 0 and 1. The even coin flip is half, of course. Theta is half. But it may be non-even, okay? So this is already an interesting class of distribution. Okay? But this is an example of parametric. So this is a very simple example. Other examples, the Gaussian distribution, for example. So a one-dimensional Gaussian, the random variable is x, real number, one-dimensional real number, and the parameters are what? There are two parameters: the mean, or mu, and the standard deviation, or the variance, which is sigma squared. Okay, so normal with mean, mu, and standard. In this case, we actually assume that there's a probability distribution function. X is real. Here, x was binary. Here, x is real. And we assume that we know the conditional probability, which is, as you all know, e to the minus x minus mu square over 2 sigma square. Okay, so this is the density function, the Gaussian density function. It's another parametric distribution. The parameters theta in this case is the vector mu and sigma, which lives in the half plane. I mean, u can be anything real, sigma is positive usually, or non-negative. Okay? There are other examples. Noga mentioned them to you. Bernoulli, Poisson, exponential, whatever. We'll see that all these nice distributions that you mentioned in the course so far have something in common. They all belong to what's called exponential families, but we'll come back to this. Okay, so they're not coincident that we talk only about this type of distribution. They have something very nice in them. Now, so the Bernoulli, Poisson, gamma, whatever. I mean, there are so many distributions. High square distribution. I mean, okay, you know them. There are many. So so we want to start. You want to start with parametric distribution, and we want to think of it as a Bayesian decision problem. So the problem is given observations. Okay, so the problem, the estimation problem, given x, or in general, we are given IID sample of size n. By the way, this notation, I should say it again. I mean, this is a vector x1 to xn sampled independently in this case. Okay, so we assume that x is sampled from this probability. That's the way we denote it, and so it's a random variable, and the problem is to act in a good way, to estimate. So we know, this is called the family, the parametric family. So it's not one distribution. There are many possible states of theta. So let's say I know that the weight of people is more or less Gaussianly distributed. Though it's usually positive, but still we assume it's Gaussian, it's a mean. So it's we don't know. We want to estimate the mean and the variance. How do we do it? Of the true distribution. In other words, we want to learn the model. Okay, same thing. So estimating theta. So the action here is going to be some decision function, which means what? Tell me what you think about the best theta. So it's going to be an estimator, which is usually going to be a function of the observations. Just like our decisions in Bayesian decisions. So this is called an estimator. By the way, in Hebrew we call it either משערך או שערוך פרמטרי עם עין, או עומק או אומדן. Sorry, go back to English. So estimator. Now, what do we need in order to make Bayesian decision theory? To make sense of it? In what sense we want theta to be good? Okay, so theta is our action. This is analogous to action. So we have a model. In order to actually apply our Bayesian decision theory to estimation, we now make the following analogy. So omega is now theta, the space of parameters. So the state of the world, state of omega or whatever world, is the space of parameters. This is a big jump. I always talked about two states of the world. Now we have a continuum. Multi-dimensional continuum. Okay, it sounds like scary, but it's not. Actually, if I really assume to be continuum, then I have all sorts of analysis tricks that can help me. We'll see it immediately. Not only that, I usually want to assume that the probability, it's a continuous function of the variable theta. Actually, I even want it to be differentiable twice, usually. So I assume that the parametric family is twice differentiable, which means d log p to d theta and d square log p to the theta square exist. I need them. So it's not only that I assume that theta is continuous, I assume it's now continuum. I assume that all the things that I want to care about are continuous functions. If you think about the examples I had before, let's say the Bernoulli and the Gaussian are both continuous differentiable functions of the parameters. Okay? So this is usually the case. If it's not the case, we have to be more careful. It's not that we can't do anything, but we have to be more careful. Okay, but in order to actually apply Bayesian decision theory, what should I do? I need two things. Actually, I need a prior. Okay, so I need a prior over theta. This is a big headache. But I want to assume some prior over theta. In estimation theory, it's not always clear where do we take this prior from, so we take convenient priors. That's usually what we take the priors that make sense, that make things easier for us. But we actually try to get rid of this assumption if you can, but not always. The other thing that I need is what? What is it? The cost function, that's right. So I need a lambda, which should be a function of what? The action and the state of the world. In this case, it's a function of theta hat, and there is theta. Okay? This was the state of the world, and this was my action. So I need a cost. Cost, in this case, actually is more often called loss. Loss function. Regret, there are many names for that. Okay, it depends on the context, but okay. Actually in RL, we like to call it value because we want to talk about positive things, not negative things. It doesn't matter. Okay, so now I have everything, and I just need to apply my theory in principle. So let's. So the first thing I want to do is to take the simplest, to talk about Bayesian estimators as Bayesian estimation theory, as we call it, with some certain loss. So essentially everything now is going to depend on what is my loss function, or my cost function. So the natural one, for those who learn something somewhere, linear systems, the mechanics, the natural loss function is something that should be positive, and has a minimum when theta hat is theta. That sounds reasonable, okay? So what is the natural thing for that? So the first and the most common, and very important one is what we call the square loss. Square loss, or L2, or quadratic loss. So lambda of theta hat and theta is simply theta hat minus theta squared. That's a nice function. Why it's a nice function? Smooth, differentiable. We know everything, and the derivative is linear, so it's going to be easy. If this doesn't work, then we don't know anything. Okay? By the way, if it's a multidimensional parameter, so we take norm, the L2 norm, the sum, the multidimensional generalization of this. Okay? Okay, so what do I want to do with, in this case, what's the Bayesian optimal? So the best optimal decision, I don't have to rewrite the whole theory. What is the best decision rule? The one which minimizes what? The conditional risk. Remember? Okay, so I need the conditional risk. So what is the conditional risk? So the conditional risk, in this case, R of theta hat given x. Yeah, well, so that should be squared. Is what? So I know it's the expectation of the risk. Well, I assume to remember something from what I said before. So it's expectation of the risk conditioned on my observation, average over what? Over the state of the world. Okay, so it should be an integral because theta is continuous. I don't have sums anymore, but integrals are much nicer than sums in many ways. So I should have integrals over all the states of the world. So in this case, it's the parameter theta. The conditional, the risk. What is the risk? So it's theta hat of x, whatever it is, which is minus theta squared. This is the risk at x, at observation x. Okay, that's what I said. And multiply average over what? Over the state of the world, which is the probability of the state of the world given the observations. Okay, that's the conditional risk. How many of you actually looked at Amir notes of the third lecture? If you didn't, you should. It really will help you. Because I'm just following it very quickly now. So, what should I do in order? So my optimal base optimal is what? Is the theta hat that will minimize this. Okay, so whatever it is, I don't know what it is yet, theta of hat. But I want the argmin. I want theta hat Bayesian L2, whatever. So it's base optimal with respect to the cost L2, which is the quadratic cost. Okay, so this is a funny notation, but it will help me. So of x is simply the argmin. So whatever it is over all possible functions here, the argmin over all possible theta hat of this R theta hat x. This is always true. But in this case, this is a continuous function of theta hat. You see why? Because a theta hat, I don't know what it is. Actually, I don't want to think about even the depends on x. X is going to appear here. Theta hat is a number I don't know yet. Given x is some number. Okay? So it's a bit confusing, but it's all right. So this is going to be the choice of theta hat at a given x is the one which minimizes this integral. How do you minimize such a thing? Select derivative to 0. That's the first thing you do. I mean, and then later on worry about its minimum or maximum. But since it's a parabola, it has a minimum. I don't have to worry too much. Okay. So you take the minimum of this. How do you take the minimum? You take the derivative. Since I assume that the domain doesn't depend on theta hat, I can integrate. I take the derivative inside the integral. Is this clear? Why I should worry about it? I mean, so I want the derivative. I want the derivative with respect to theta of r theta given x, which is the derivative of this integral. So to theta hat. I'm sorry. Theta hat. Theta hat is not the variable of the integration here. It's just a number inside the integral, so I can take the derivative inside the integral. There's nothing, as long as this doesn't depend on theta hat. If the domain depends on theta hat, then you have to think about it a little more. You can just another term that you have to worry about. Okay, so it's very simple. It's 2. The integral of so the derivative of square is 2 times the linear. Okay, and so it's 2. The integral d theta of theta hat minus theta p theta given x, and I want this derivative to be what? 0. So this is the solution to this equation. This is going to find the minimum. Okay? Very simple. So just a trivial algebra. The first integral is just theta hat, because theta hat is not theta, so the integral over theta is 1. So what I get from it, allow me to write it here, is the theta hat is the what we call posterior expectation of theta given x. Or this is not sometimes called the conditional expectation, the conditional posterior or the posterior expectation. Posterior expectation, or posterior conditional expectation. A conditional mean, you're going to see this as well. This is the famous conditional mean. So it's actually very, very intuitive. The one which will minimize the square loss is simply the average conditional observation over all possible theta. Now, I don't have time, but you should see some examples of this. So Noga is going to show you one. For example, in the Gaussian case, it's also written in the notes, or in the Bernoulli case. So I need to assume something about priors of the Bernoulli variable. But as you're going to see, I want to jump So this is something to work out in simple examples. In the Gaussian case, it's going to be simply the sample mean, if you want to estimate mu. In the Bernoulli case, it's going to be, again, the estimate is going to be sample mean. And you're going to have this posterior is going to eventually peak. And we'll talk about it next time. I mean, this is going to be central, as long, when x is now not one sample, but IID samples, this thing is going to get sharper and sharper, as you already noticed, because of the self-averaging thing. And eventually it's going to peak like a Gaussian around something.
So what's going to get sharper?
The posterior. When there are many observations, the posterior is going to be sharper and sharper. We'll see this explicitly next time. But I just want to jump a little bit to show you what actually happens here is actually much simpler, in some sense. So, okay, expectations, that's nice, but this posterior expectation, for those who actually do these things, in high dimension, it's a headache. Because I need to integrate over many dimensions, or I need to do all sorts of... Okay, so there is another cost. You remember the cost that actually I like very much, the one that gave us the probability of error? What was it? Yeah, it's going to be maximum accuracy in a second, but what was the cost? So it was 1 minus delta, remember? 1 if I'm in the wrong state, 0 if I'm in the right state. Okay? That's a very natural cost. It's actually, so this is called so if I take this cost to be, I want 1 minus delta for Kronecker. The only problem is that theta is now a continuous variable. So if you're a physicist, you don't think twice. You replace the delta of Kronecker by the Dirac delta, and that's it. So it's essentially 1 minus the Dirac delta of theta minus theta. Okay, if you don't understand what it means, this is a simple generalization of delta theta theta hat that I had before. So it's 1 if they are different. It's 0 if they are different, and it's 1 if they are not different, and 1 minus this is precisely what I want. It's going to penalize whenever I don't have the right theta. This is, in some sense, the most natural loss. Whenever you don't give me the right theta, I give you penalty. Okay? The same penalty. Now,
if it's binary, if your possibilities within are binary, but if it's a continuum, then you can be less right and more.
You're right. So at this point, let's be formal, because I have no time. And just take this and see what happens. Now, as anybody who learned anything from me knows that whenever you see delta function, you always have to think about an integral. They always go together. Delta function outside of an integral doesn't make sense. But inside an integral, what does it do? It simply takes the value for which the argument of the integral at which the argument of delta is 0. Which means it's sampling the integrand function. The integrand. That's why they sometimes call it a point sampler. It takes out of the integral just the one. So if you do the same thing that I did here with this loss, what do you think will happen? So I replace this with 1 minus delta. And what will happen? So the 1 will integrate to 1. And the delta in the integral, what will it do? It will pick up exactly the value for which this is 0. So in this case, we don't need to take derivatives. The risk itself is just to argue at this theta. But then if I want to minimize the loss, this should be simply what we call the theta estimate maximum a posteriori, which is the arg mean, or the arg max, I'm sorry. I want to minimize the loss because of this minus is going to turn into a max. The arg max of the posterior probability. Okay, of opposite. This is the same. This loss is trivially plugged into the integral is giving us simply giving me the point. The delta is going to pick 1 minus the point p theta, but then I want to minimize the loss because the 1 minus is actually maximizing this minimizing losses, maximizing. So this is called the maximum posterior. MAP, maximum a posterior. Very important to remember. But just on one more line, notice that this is the same as maximizing the log of the probability, because log is just a monotonic function. Okay? But the log, this is the log of the prior over theta plus the log of the likelihood. We saw this already. Now, in the case of IID of many observations, so this is very easy. I should maximize the prior, take the derivative of the prior. The derivative, the max of the derivative, you have to do it carefully. But when n is large, this is going to be negligible. This is going to be a product. So this is going to be the sum of the log pxi given theta. So this in principle is going to grow linearly with n on average. So for n is large, the prior is completely negligible, whatever it is. So we saw this already. So this is going to be very similar to argmax of p, of log p, of xn given theta, but this is called theta maximum likelihood. Okay, so you see that for n is large, the prior is small, or it's negligible. Negligible. Whatever. Negligible. And this is enough. And this is really important. So this is the definition of a maximum likelihood estimate. Maximum likelihood, this is the simplest thing I can do. So you see this is an approximation of the maximum a posteriori, which is, and I'm going to show you, there's also an approximation of the conditional posterior, at least in the case where the distribution is actually going to be centered around the peak, and the peak is the maximum likelihood. And so this is what I'm going to show you next time. So in practice, this is the most useful thing to do. To take the theta, which maximizes the likelihood of the data, of the evidence. So you see, this is a very simple extension of our Bayesian decision theory to parameter estimation. And you see, okay, so we learned one thing and the same thing, just good mathematicians. We solved one problem and we just turned the other problem into the first one. And we now know how to solve this one. Okay? So it's very simple. Please, do me a favor, read the Amir's note. Now, about next week, I will probably be here, because I'm not going to miss too many classes. I'm already behind schedule as far as I'm concerned. I'm not sure how many of you will be here, but...
Can you switch maybe with at least those who won't be here, who won't miss the lecture?
Switch with Noga, which means Wednesday instead of Monday. This I can do, no problem.
It'll be better.
Unfortunately, my travel plans have completely messed up. My wife is hospitalized. I'm not going to travel this Thursday. I'm probably going to, I hope to travel next Thursday. So next Monday I will definitely switch. I'm not sure, by the way. Maybe I will attend on Sunday. But anyway, so as far as I'm concerned, next week is normal, but I'm willing to switch. That's easy. Okay, and Noga will give you plenty of examples of how to apply this. All right, see you next week.